Okay, let's talk about hyperbolas and ellipses. And we'll kind of go through some of these. This is continuing our discussion on trigonometry. So ellipses. Where's my... Oval isn't a well-defined term, right? Egg shape, not really well-defined. So we need something that is well-defined. Oval is ellipse-like. So an ellipse is a symmetrical shape. So an egg isn't an oval. So to be clear, oval can be let's try that again. Oval can be an egg. Oval can also be very symmetric. Eggs aren't symmetric. They're just truly not. So there is some symmetry to them, but they don't hold that one end of the egg is as thick around as the other end. So it doesn't quite work. So an ellipse is symmetrical, though. So circle, the set of points in a plane such that the distance from a fixed point is the center, usually we say is the center, is constant. So an equidistance from the center is a circle, right? The circle is not a disk. It is everything outside at the edge, right? It's that edge, like a ring. An ellipse is a set of points in a plane such that the sum of the distances from two fixed points is constant. We call those two fixed points foci. So the constant distance is 2r, is defined such that 2r is greater than the distance between the foci. Okay, so the distance between the two, let's see. Not that. Is that the right one? No. Okay, so I have two foci. Wow, that is such a rough sketch. But this distance here, between here and here, is less than the 2r distance from here to here, right? And as we move along, whatever the sum of this distance and this distance is, as we move along this shape, that particle should be constant. Okay, now my sketch is really bad, so we'll look at a better one. So here we have two foci, two focuses, right? Foci is when we're talking plural. A focus is each individual. So here's one, here's the other. And I have distance 1 and distance 2. The distance 1 plus distance 2 is constant. As I move this way, it gets closer to this focus, but farther from the other. And as I come back around, it'll do the same thing. It'll get closer to this focus and farther from the other. But that distance 1 and distance 2, will always equal the same thing. The segment from the center to the vertex, so a center is between your two foci, wherever it is equidistance between the two foci. And the segment from the center to the vertex, so from here to a vertex, is the major axis, semi-major axis. The major axis is from one vertex to the other. And then we have a semi-minor from the center to the end point of the minor axis. And that is called the semi-minor axis, and the whole thing is called the minor axis. So just to be clear, those pieces are important. So there's an ellipse. We need to talk about the equation. You guys know the equation of a circle, so yeah. We want the equidistance to our x naught, the distance to x naught, y naught, plus the distance to x1, y1 to equal 2r. And that will determine where our foci are. Foci centered on the origin, like this one here has the added benefit that whatever our first focus is, the other focus will be a negative version. So it'll have the negative x. So this would be a positive x. This would be a negative x. For a foci on the x-axis, center at the origin, I think I said that, we have this formula, x squared over the radius squared plus y squared over the radius squared minus the focus squared. Now, I want to be clear, because we're squaring f, right, we don't really care which focus we use. You use the negative one, it's going to come out to the same thing as the positive one because we're squaring it. And this should sum up to be 1. And they're determined by the focus and the radius. F is a real number, greater than 0. That's pretty much what we know. The major horizontal axis, centered at the origin, could use this formula, x squared over a squared plus y squared over b squared is equal to 1, where a is our vertex, our x vertex here, and b is our y vertex. And again, since we're squaring this, those don't really care which one. We just pick one because they'll be an equal distance. So that's always useful. A must be greater than B. Otherwise, it's actually not centered, and it's not got the x-axis as a major axis. It's got the y-axis as a major axis. And it uses these vertices. I mentioned that. The major axis has a length of 2a. Right, because the distance from the center to here would be a, and the distance from the center to here would be a, so 2a. The endpoints, the minor axis, are b and negative b, so same idea. We have change the color on this one. We have b distance and b distance, so 2b. That's why I don't like that one. Minor axis 2b, b is the center, so yeah. The foci is at c and negative c, and in this case, c squared would equal a squared minus b squared. So c is the distance. So if we took the major axis distance, 1/2, the semi-major axis, I guess, semi-major, so this piece here, and then we took the semi-minor axis, that piece there, we square each of them. The distance for c would be, and this is c, right, that's c, this is the negative c, would be that. So we have a bunch of these formulas. So we have these two here, and we have this one here. C is representative of F, right? That's representative of our focus. And our A is representative of A. So we can look at these and we could see how we could replace them and change them up. So the set of points, hyperbola, set of points in a plane such that the absolute value of the difference of the distances from two fixed points, the foci, is constant, or the differences of the distances from the two foci is plus or minus 2r. Hyperbolas work kind of the opposite of ellipses. A lot of people think of them as kind of the opposite of circles, but they're more opposite of ellipses. So we have two foci, here and here, and our vertex is now inside, and these open kind of reverse. Instead of opening and circling this way, right, with the vertices being out here, this opens and it creates this never-ending arc, if you will. And we have a transverse axis which is the axis that goes from one foci through the other foci, the line that goes between the two foci. And the vertices are always on those. It doesn't matter which way it's shaped. So here we have one shaped the other way. Same idea. Now there's some relations to this, to the ellipse, that we're going to talk about. So let's look at the equation of a hyperbola. Distance 2 x naught y naught minus distance 2 x1 y1 is equal to plus or minus 2r. Remember that the other one was adding them to equal 1. This is a little different. The foci on the x-axis and the center at the origin follow this pattern. X squared over r squared minus y squared. This time f squared minus r squared is equal to 1. Last time it was r squared and f squared, and it was the plus. So keep that in mind. And these are determined by the foci and the radius. So same idea. We're kind of manipulating these ideas. We have that the transverse axis, the horizontal, centered at the origin, has this nice equation, x squared over a squared, where a is the determination of the vertex. This applies to this, the vertex. And c is our foci, right there. And for hyperbolas, either a or b could be greater. A is just the denominator on the positive term. The vertices are at negative a and a, because we're centered at the origin. We're not always centered at the origin, but in this case we are. The transverse axis has a length of 2a. A is the distance from center to vertex, right? So from the center here to our vertex here is a. So it makes sense that the transverse axis, which is from one vertex to the other, is 2a. And the foci, again centered over here, has a distance from the center. C is the distance from the center to each piece. So c squared is equal to a squared plus b squared. Yes, that does sound like the Pythagorean theorem. It's almost like trig uses that. So asymptotes. Hyperbolas have asymptotes. If one is centered at the origin, the transverse axis horizontal creates an imaginary box. Asymptotes are imaginary. They don't really exist, but they're often useful to draw our lines. Same idea with this box, and this box has a relationship that, oddly, this point, which is in line with the center, and this point become the end points of our box, with the vertex being the end horizontal, and then we have end verticals. And the dashed line here, this is our asymptotes. No matter how big our parabola gets, this line continues. And the asymptotes pass through the center and corners of the box, of this imaginary box. And the slope is, of course, rise over run. So the slope has this relationship that it is b over a and negative b over a. So the positive slope, b over a, negative slope, negative b over a, right? And we can write them using this idea, okay? Now again, this is centered at the origin. We're talking about a very specific one because they're not always centered at the origin. But we could always use what we know and find b, find a, and figure where the center is. Right hyperbolas are special, just like right trigonometry is special. And we have the relationship that right hyperbolas create a perpendicular line with the asymptotes, which is very different. If the hyperbola whose asymptotes meet at right angles, it's considered a right hyperbola. And this occurs when the focus is at r square root of 2. So whatever that r is, it becomes the square root of 2. And then we have this question. You guys have this question on your homework. Looking at this formula, look at this one. This is the great one here for this. We're studying hyperbolas, and we're using this particular equation, 5.7. And what happens to the asymptotes if r approaches 0? And they want you to sketch a typical hyperbola for which r is very small, right, if r is approaching 0. So using what we know, and we could manipulate this. You guys love to manipulate. So manipulate this and see what your slope would be if you manipulated that to solve for r. You should get something that looks similar to squared over r. But again, r is getting closer to 0. So we have to consider what's happening. Well, as this r in the numerator, this r up here, goes away, right, it gets closer and closer to 0, the result of f is going to go up, right, because there's less being taken away from it. So whatever f is, it's going to be closer and closer to f, right, which is the focus. The problem is this r gets smaller, right? So while the f is getting bigger, the r is getting smaller. So when that happens, this number is going to become bigger and bigger. So if r goes to 0, so maybe we write something like, if r goes to 0, then the asymptote, right, that's too much to write, goes to infinity, right? This is getting closer and closer. So they'll tend to have something that looks very close to the y-axis. So on a standard graph, right, just a standard graph, I would have things that would look something like my asymptote, or my foci, or the shape of it, of the hyperbola would look something like very steep, because this asymptote is going to be closer and closer to infinite. It's actually getting closer and closer to the y-axis. So something along that lines, this is my x, this is my y, right? Put arrows on them so we're proper. If what happens if the asymptote of r approaches f? Well, if r approaches f, then this square root is going to go to 0. Well, doesn't matter how large r gets down here, if the top is going to 0, we're going to have kind of the reverse idea. So this is y, this is x, and my hyperbola is going to be very, very sharp. Pretend these are all equal. I'm not using any measuring device, right? And the asymptotes are going to get closer and closer to being 0. So we might say if r approaches f, then again, too much, goes to 0. So that gives you an idea on that one. Write it out. I mean, clearly that's part of this exercise, is how you would explain this to someone else. So how you would write this. Is that the only? I think that might be the only question in 5.1. Let's see. Yep. All right. We'll continue the rest of this next time.